Okay, so in this lesson, I'm gonna go over some of the concepts covered as far as amplitude modulation is concerned. So remember, when we talk about amplitude modulation, there's a couple things we need to discuss first. Um, the fact that the human voice cannot be transmitted over into space or into the sky or propagated. Because there would be too much interference. Okay, there's too much stuff that falls within that. Not to mention that the ground and everything else would interfere with the signal. So we can't just propagate our voice. And so what some ingenious people did and what they came up with is we need to grab a higher frequency called a carrier frequency. Okay, carrier frequency. So we have our signal. So this is my voice, okay? And I want to transmit it through an antenna and propagate it into space, right? Or the sky, or through any amount of distance. So what do I need to do is I need to basically, so remember as far as what electromagnetic propagation is, or what that means is basically when you put enough potential and power, you can propagate waves. And the waves you're propagating are electric and magnetic waves. They're 90 degrees apart, and they propagate in the direction perpendicular to the direction of the field. Okay, so this is what our goal, our end result is. We want to combine these now, because I basically want to be able to propagate higher frequencies. So it turns out higher frequencies propagate much better than lower frequencies. So in order to solve this issue, I must propagate or find a way to, the word term is going to be envelope, right? To put this, combine these two and send them off into space. And if I were to combine these two just across a linear device, such as a resistor, this is the waveform you would get. Okay, this waveform does not propagate through space correctly. Okay, it won't sound right. This won't carry the intelligence like we want. So that's why when we do it, we need to do it through a nonlinear device. Okay, so an example of a nonlinear device would be a transistor, or this kind of reaction that we have here, right, between the diode and the tank circuit. So we have a capacitor inductor acting at tank circuit. Now remember, to find if I want to figure out what this guy is going to propagate, or what the frequency of this is going to be, you can figure out what the resonant frequency of the tank circuit by just 1/2 pi, right, and the square root LC. Okay, so that's your resonant frequency. And keep in mind that if you wanted to change this, right, you can increase or decrease your inductance or capacitance, and you can that'll increase or decrease your resonant frequency. Okay, so when I combine the signal, so in this sense we have our modulated signal and our carrier signal. Okay, so notice that I combine them like we would normally at this point. That would, at this point across R3, you're going to get a wave like this. Okay, across R3, that's what R3 sees. Now, what we do with that is we clip it. Okay, we clip it such that notice that we get this wave here. So I combine this and this, you get the same wave. Now, the only difference between this one and the one shown here is the fact that this one's just a higher frequency, right? You see it's much more compressed, suggesting it's a higher frequency. Okay, so when you combine the two, you get something like this. Now, all you do is you cut the top portion using the diode, right? And what that does now is it's going to trigger the tank circuit only on the peaks, right? So what it's going to do, it's going to charge the capacitor, right? And then we're going to get a bit of a flywheel effect. In other words, so when this potential shows up, charge the capacitor, capacitor's charged, then it discharges, right? And then we get the opposition from the inductor, creating this result, right? And it fills the void. Then the capacitor charges up a little more, and then it discharges, and then the capacitor, the inductor opposes that, and you get this flywheel effect from the tank circuit. And that becomes your output. And this, my friends, is an amplitude modulated signal, okay? Now notice we call it amplitude modulated. It's because it's running at the same frequency, but its amplitude is changed throughout. Hence amplitude modulation, okay? Now, when we look at the signal as to why exactly do we have certain portions of the signal that is